Okay. Okay. So this is a session 6. So in the last session, this is a continuation of previous session. So where we talked about groundwater basics. So we will start with the same. And we'll proceed towards solving the study flow cases in confined aquifer. So today we will solve two important gate questions. Like I have taken only two because the model is same, and the questions from the same model are coming in every year. So let's proceed with that. Okay. If anybody is unable, unable to hear me, unable to see the slides, you just stop me. I'll reconnect. So let's start with the same basics. So in the last session we is talked with what is a specific yield and what is a specific retention. Again we'll go with that. So first, before introducing the specific yield, I even talked about a porosity, which denotes with eta, which is nothing but ratio of volume of voids to the total volume. Okay. And so with this we have started in the previous session. We proceeded and we solved few questions on our porosity as well as specific yield. So today also we'll solve one question which recently came into the gate for 2 marks on very simple concept of specific yield only. We'll solve that question and in a very simple manner. Okay. So what is a specific yield? A specific yield is defined as the volume of water released from a storage by an unconfined aquifer. So it can be confined as well as unconfined. So from the book I have taken, it is written as unconfined, but it is valid for both. Unconfined aquifer per unit surface of area of aquifer per unit decline of the water table. So essentially, suppose if you take a 1 meter cube by 1 meter cube by soil. So 1 meter, 1 meter, 1 meter. Suppose if you take this is the soil sample. So soil sample, initially the water is the soil sample is fully saturated, like a fully saturated. So what happens? Suppose like let's say you took some, like you have taken some water from this particular soil sample. Let's say this could be delta W. So because of this, initially the soil sample is full up to here. Now that it has reached to this level only. Okay. So now it is nothing. So it has reached to this level, and initially this is 1 meter. Now it would be like a one minus some delta x meters. Okay. So now suppose like now how we can calculate specific yield? Specific yield nothing but area. Suppose if we take this is 1 meter, the total area is how much? 1 meter, 1 meter into 1 meter into delta x divided by 1 meter into 1 meter into 1 meter. So why I have used the delta x? Because this much only of water we have taken out from the soil sample from the 1 meter by 1 meter by 1 meter confined aquifer. So in this way we can calculate the specific yield. Okay, am I clear? Like, so let's solve one question. So this is this I have taken from gate 2020 CE set 1. The question is as follows. In the similar type of question we have solved in the previous session also, but that is from 2016. So now I have taken another question from 2020 to show the importance of this particular model type of question. So in a homogeneous unconfined aquifer of an area 3 kilometer square, the water table was at an elevation of 102 meter. Okay. Initially, the water table is at 1 or 2 meter. After a natural recharge of volume 0.90 million cubic meter. The water table rose to 103.20 meters. Okay. After this discharge, the groundwater pumping took place and the water table dropped to 101.20 meters. So the volume of groundwater pumped after the natural recharge expressed in million meter cube and round it off to two decimal points. So the essentially the question is like this. Okay, this is a case situation one. So and this is 102.0 meter. Now what happened? You have added zero point 0.9 million meter cube water. Because of this water level became this. Okay, which is 103.20. Okay, now what happened after some time we have taken out some amount of water, some V amount of water. Because of this, the water level reached to this particular case, which is 101.20. Okay, now the question is how much volume of water pumped from this soil, from this area. So can anybody guess how we can calculate? So area is 3.0 kilometer square. So one can convert into, suppose it can be written as 3.0 into 10 power 6 meter square also. It can be written in this. Anybody has an idea how we can solve this question? Just you can guess it. Uh, so like how we can start this, how we can solve this question? Any, you can guess it. Maybe it can be wrong, but you can still try. So I have given a hint also. Specific yield is a given. Specific yield is given as ratio of volume water recharge slash drain to the volume total volume of saturated aquifer. So in this case, actually this question is for a 2 marks question. So this question contains two steps. One is that to calculation of specific yield SY. By using that specific yield, we can calculate the groundwater pump from that. So how essentially we'll do. Okay. So what is the Q here? Q is area into, suppose Q is nothing but volume of water, VW equal to area into delta W. So how much water, delta H. Suppose here delta H is a change in the level. Okay. Okay. So in the first case, what happened? Like let's say first case we can say as a recharge. First case we can say as recharge. So what is viscosity yield? Is nothing but volume of water drained or recharged with the total volume of saturated aquifer. So here what is the volume of water? zero point 0.9 into 10 power 6 meter cube. So this much volume of water added to the soil sample. Because of this much, like how much volume of total saturated aquifer happened? 3 into 10 power 6 meter square into 103.20 minus 102.22 meters. This is the total volume of saturated aquifer. Okay, and this is the volume of water added to it. So this is a zero point 0.9 and this is a 3.0. So by doing this, you can get a specific yield as 0.25. Now we will use this specific yield and we'll calculate the volume of water drained from the total volume of saturated aquifer. Okay, fine. So what is the total volume of saturated aquifer here? It will be 3 into same area will be the same into aquifer into 103.20 minus 101.20 because so this is a initial this is a starting point for the second case. From these two we reach to this particular third level. So this much as a saturated aquifer area has changed. So this is a total saturated aquifer volume. From this saturated aquifer volume, some amount of water will be taken out. And so why, like, it may be confusing for you, like why we have taken this is a 103.20 minus 101.20 as a volume, because as you know there are two terms. One is a specific yield, another is a specific retention. Specific yield is the amount of water drained or recharged to the total volume of water, whereas a specific retention will be amount of water still retained even after the drain from the soil sample or saturated aquifer. So there is a two terms, like one is SY, another is a SR. So there is some amount of water left in the saturated aquifer, even though suppose you have recharged after the recharge of 103 point centimeter. So we pump from this particular aquifer. So because of this pumping action, the aquifer can only able to give this amount of water per a unit width, per unit drawdown. So that will we need to calculate. So this is a 0.25. So VD equal to 0.25 into 3 into 10 power 6 kilometer square into this will be 2 meters. Sorry, this will be like water put it 10 power 6, it will be meters square only. So it will become 15000000 meter cube. So but in the question they asked to express in terms of million meter cube. So what is a million? What a million? 1 million equal to 10 power 6. So you will write in this way. Answer will be 1.5 million meter cube. So let's see the solution. So what I have taken, so I divided the question into two parts. One is a recharge part, another is a pumping part. So this is a 2 marks question. Obviously, the 2 marks question will require some effort. Okay. So first, what you will do by using the given information, you will calculate the specific yield. So specific yield is nothing but the amount of water will be given by the aquifer per unit drawdown the per unit drawdown. So first what you will do, you will calculate the SY. SY will be like volume of water recharged to the total change in the volume, like 103 minus 103.20 minus 102.00. So it will become as 0.25. So use this specific yield. Sorry, here it is 25. Use this specific yield 0.25 and calculate the volume of water pumped from this aquifer. It will be like total volume of saturated aquifer into the specific yield. So it will be 303 into 10 power 6 into 103.20 minus 101.20 into 0.25. 0.25 is the specific yield. Okay. So in this case, in the similar manner, we can calculate the volume of groundwater pumped after the natural recharge. See, in this case, you just need to draw in this way. First case, what is the first level? So after recharge, what happened? So the level increased. After pumping, the level is decreased. So in this way, if you write it down, it will be easy for you to solve. So in this manner, you will divide the question into two parts. This is the first part, and so this is the second part. And see, if you look at this question, it's solved very simply. Like only two steps are there: SY and Q. By performing these two steps, you will able to score 2 marks here. Okay. And the similar type of questions are been like appeared in the gate 2016, 2018, and 2020, and now 2020 also. Maybe I did not see the 2022 paper, so 2021 paper. Maybe if I'll see the 2021 and I'll update in the next section. Okay. So this is about a basics of groundwater flow. Now let's imagine this is a rock stratum. It's a rock, and this is a ground level, not groundwater, ground level. This is a groundwater level, GWL, groundwater level. Okay. Now let's say you insert a well. This is well. Okay. Now you inserted a well, and it is touched at the bottom of the rock stratum. Okay. And water will enter into this in this manner, radially into the well. So before proceeding further, can anybody identify what type of aquifer this is? What type of aquifer? This is one at the bottom it is confined, and at the top surface it is has a free surface. Can anybody say what type of aquifer it is? So it is unconfined aquifer. Okay, as I mentioned in the previous session, confined aquifer will be confined from the both the sides. Unconfined aquifer will have one side free surface. Okay, let's say this is a well, and this is a well. We inserted a well into the unconfined aquifer. Okay, so this is a initial level. So as suppose before pumping, the water table is at this level. This level is called static level. Let's say static level. Now what you do, you pump water at some rate of QT. So what will happen? Slowly the water in this well will draw down, and slowly in this way it will draw down. Okay, so at any time t, the water level in the well is called pumping water level. Okay, so at initially it is here one, and after some time it will become here and the third. Like as we progress, as we pump more and more, it will the water level in the well will decrease. Water level in the well will go down, but the aquifer will supply a water to the well at a rate, at some rate, maybe that some rate of q. Okay, at some rate of q. Okay, so at any time t, the difference between the static level s, let's say this is mentioned as s and this is mentioned as a p, so s minus p indicates drawdown in the well. Okay, drawdown in the well. Okay, so and this drawdown, this s minus p is a function of pumping rate qt and aquifer property qt, this small qt, and as well as um, and as well as a duration. Let's say if you pump this well for a very long time, pump water from this very long time, then this s minus p will reach to the steady state. Okay, it will reach to the steady state. In that case, s minus p will have a different perspective. See, why I'm all this teaching that, because I need to give the feel of what is a cone of depression. So to understand the cone of depression, we need to understand these few basics. Okay, so this s minus p is it termed as a drawdown, and it is often shows as indicates with the capital S. Okay, capital S. Okay, so suppose as you can you observe here, the it not only the water level in the well, even the surrounding of this well also the water level will slowly decrease. Okay, and there it will be maximum into the well, but as we move away radially from the well, the drawdown will decrease and it will reach to the static level. Okay, it will reach to the static level. Suppose if one if one look at the 3D way 3D map, Okay, suppose if I wanted to simplify, it may look in this way. So it may look in this manner. Suppose if you have, so, and suppose if somebody has a 3D diagram, it will look as a inverted cone. Inverted cone shape it will form water level. So water level in aquifer will form as inverted cone shape. So as you pump water, okay. So so this will continue, like as you pump for a certain time, it will, the water level in the well will decrease, and as well as the aquifer will supply water to it. But after certain time, after certain time t naught, the qt approximately will be equal to the small qt, nothing but whatever the amount of water you're pumping from the well will be nearly equal to this, the water supplied by the aquifer to the well in a radial direction. So it's not like one direction. I have taken as a cross section so that it may appear as a from x direction only, but it is like a radial. So it means like from all this direction it is coming radial. So in this radial manner, this water will enter into the well, radial direction. Okay, and this well has a radius of RW. Okay, suppose if when I ask what is the radius area of a circle, equal to, suppose in terms of R, pi r square. Okay, or if I ask you to what is the perimeter will be 2 pi r. Okay, keep remember these points, and we'll these formulas will be helpful in deriving the equation. Okay, so after certain time after certain time t naught, this qt approximately will be qt, and there will be a water level shape forms in aquifer of a inverted cone shape. Okay, so this will be this in this type of manner one shape will form. Okay, and this drawdown will decrease as we move away from the well, and it will become zero at a distance of capital R naught. And this particular R naught is nothing, is called as radius of influence. Okay, so at a radius of influence, at a radius of influence, drawdown is zero, that is S is zero, as well as H will be equal to the initial head only. Okay. So okay. So we know what is the cone of depression and what is the radius of flow. Cone of depression is nothing but a drawdown profile at any time t in an aquifer. So cone of depression is nothing but is drawdown profile. Okay, which is a function of all these things, okay, qt and small qt and t and all. Okay, and r naught is a radius of influence. So this is a radius of influence. Okay, so these are the two terms. All these things I have discussed. Okay, so at this instant of time, study flow condition exists in the aquifer, and cone of depression get stabilized. I told you now. So after certain time t, this qt and capital qt and the small qt will become equal to, and it will become equal, and this cone of depression will become stabilized. This equilibrium condition will change if qt either increase or decrease. Okay, and as long as we are maintaining this qt, this as the studies to after the aquifer reach to the steady flow, this q capital qt and the small qt will be equal. Okay, so For modeling this particular study flow, we made this following basic assumptions. One is that aquifer is bounded on the bottom by a confining layer. Suppose so as I've shown you, aquifer is confined below from the on the bottom by a confining layer. Okay, so ground level of the aquifer is horizontal and not changing with the time prior to the start of the pumping. So suppose there will be slopy ground, there will be any like this kind of a ground. Despite whatever the ground condition, the water level condition should be horizontal. These are the assumptions we made to model this particular study flow, and it is remain constant before starting of. This is not practically possible because sometimes there will be base flow, and with this the water will move from the aquifer, but that amount of water is going as a base flow will be negligible. So this assumption is fairly accurate, and all the changes in the position of groundwater level are due to the effect of pumping well only. Suppose though there are other things, like let's say as I mentioned base flow or a seepage, we will neglect all those things. We will assume that only ground the changes in the groundwater level only due to the effect of pumping. Okay, and all the geological formations are horizontal and infinite horizontal. See, all these assumptions will be mentioned in the question when they have given when they will give the question. So see, this is a tricky part in gate. Like what they do is that they trick this trick the assumptions and formulate different kind of numericals. Okay, so in the question they will mention the confined aquifer is infinite, horizontal extent, it has a confined boundary at the bottom and not confined boundary at the top. Like this they'll mention and they'll ask the tricky type of question. So it is necessary to know this, but with all these assumptions. And this aquifer is homogeneous as well as isotropic. Okay, and all the flow is radial towards the well. I have shown you now. So this is a well, and the flow will takes place radially from all the direction, and the groundwater flow is horizontal. Okay, suppose if you take this is a thing, if you dig the well, you look at this flow will takes place in horizontal direction only. So we will neglect the vertical direction. Okay, and Darcy's law is valid. So what is the Darcy's law? We have seen na? Darcy's law, velocity is proportional to the hydraulic gradient. So velocity of the water will be proportional to the hydraulic gradient. So the proportionality constant will be K, which is nothing but hydraulic conductivity. Okay, this could be having units of meter per day or per second. So okay, this oftenly we won't able to measure this thing directly. So we use some kind of a well testing or some different methods to estimate this q. So we will solve one similar example where our interest is to calculate the hydraulic conductivity only by using other given data. Okay, the pumping well and observation well are fully penetrating. See, I told you now. So in often we practically we won't have this hydraulic conductivity value. So to estimate this hydraulic conductivity value, we will use this pumping well as well as observation wells, and we will continuously monitor the drawdown. And by using those relations, we will calculate this Q and T transmissibility and other values. Okay, the pumping well has infinitesimal diameter, and that means the negligible storage and 100% efficient. It means that the RW, radius of well, will be much smaller compared to this radius of influence. Okay, and groundwater has a constant density and viscosity because obviously this water has a constant in density. Okay, so now let's see one specific case here. So here I'll talk about the Thames equation, which is really important to solve or to estimate the steady flow in a confined aquifer. So what is a confined aquifer? Confined aquifer will be is a confined aquifer is a confined at the both the sides. The water in a confined aquifer will be under artesian pressure. Artesian pressure, not in the natural pressure. So if you dig the well, suppose if you look at this particular picture, this is a confined boundary, and this is also confined boundary, and the soil between this confined boundary is called as a confined aquifer, and the water inside this confined aquifer will be under the artesian pressure. Suppose if you insert a well, you see as you inserted the well, the water level is reached above the confined above the aquifer level. So because of this influence of artesian pressure, suppose if you dig similar kind of an unconfined aquifer, the water level will be equal to the surrounding level. I mean to say that, let's say this is a confined aquifer. If you dig the well, the water level in the well will also be remain the same unconfined aquifer. Okay. So that is the difference. So in confined aquifer, the aquifer is confined from the both the sides. The water will be under the will be under the artesian pressure. Whereas unconfined, it is confined only from the bottom side, and the water level in water in this particular confined unconfined aquifer under the atmospheric pressure. Okay. So additionally, before we have seen few assumptions about this study radial flow study flow. Similarly, we need to make two more assumptions to solve for confined aquifer. One is that the aquifer is bounded on top as well as the bottom. I mean to say confined at the top and bottom both, so, and there is no leakage, absolutely no leakage. Okay, so it's kind of aquifuse kind of a structures are there. So this can be these are boundaries may be aquifuse. What is aquifuse? We discussed. Aquifuse can be a rock which have no pores, no permeability. It is like a absolutely no zero discharge and zero storage. Okay, and this well is pumped at a constant rate, and this QT is not vary the time is approximately equal to Q. Okay, it is nearly Q. Okay, these are the assumptions. Now let's do the derivation. This is an I'll quickly go through the derivation so that you will get the essence of it and from where we have get this equation. So as we know, K equal to VI from the Darcy's law. Okay, what is I here? Hydraulic gradient, which is nothing but dH by dx. But in this case, we are talking in the terms of radius. Okay, so this we approximately get written as dH by dr. Okay, so nothing but see it only shows the I is nothing but hydraulic gradient in the flow direction. Okay, here the flow direction is radial, so that's why we have taken as dr. Suppose the flow direction is only a horizontal, then we may take as the dx or dy according to the direction of the flow. Okay, so what is a q equal to a into v. So what is the area of the cross section. Okay, area of the cross section. So here, and which is not, it should be normal to the flow. Okay, it should be normal to the flow. Okay, so as we seen, this is a well, and this is in this manner the water is entering. So what is the length of water entering is 2 pi r. And what is the depth, what is the depth it is entering? It is b. So 2 pi r into b will be the area. Okay, this is area, and this is a velocity k into I. This is I. Okay, k into I. So these are time all these formulas are shown here. So then let's solve this thing. So so what we do, let's consider two observation wells which are installed in an aquifer at a distance of r1 and r2. As I have shown here, we have installed two wells like one is here, one is here, r1 and r2, from the sorry two wells like this one and this one from r distance from the observation well. Okay, with the hydraulic heads of h1 and h2. Now just reshuffle the terms. We have seen this is a sorry, we have seen this is a equation. Now what we do, we just reshuffle the terms, and now we would like to consider, like we would like to estimate. Suppose here what we do is that so this is we know that q equal to 2 pi r into b into k into dh by dr. But what is the problem? We don't know the head equation. Head equation we don't know. Okay, so what we do is that we will use this approximate method, approximate numerical method, to calculate this particular q. Okay, so integral h1 to h2 dh equal to q by 2 pi kv into r2 minus r1 dr by dr. So let's say h1 is hydraulic at r2 and h2 at hydraulic at r1. So it's equal to q into 2 pi kv into ln into r2 by r1. So you know how we got ln. So integration of 1 by x equal to ln of x plus c. Okay, here we can neglect the condition. Integration of c dx equal to, suppose here dx x dx. Okay, sorry, x plus c. Okay, this is the case. Both the sides arbitrary constant can be cancelled. Okay, so from this we have got this particular equation in an explicit form. So this is a final equation. Okay, so now alternative what we can explain, what we can do is that rather than putting into h2 h1 and h2, which is the hydraulic head, we what we do, we'll measure the drawdown. It means that suppose when we insert the well, this is the level and this is the ground level. From this ground level, how much drawdown is there? We often in the practical we measure this one and not h. So we will write it in this way. So replace h1 h2 with h2 and h1 is with s1. Okay, this will be s1 minus s2 divided by ln into r2 by r1. Okay, okay, this is a general equation. This is a general equation for steady radial flow in unconfined aquifer. So let's assume, sorry, suppose if we consider first observation well is located at a distance of rw. Suppose like rather than what we do is that uh, we will take one well. This is confined aquifer, and this is another well. Okay, and this is a well, pumping well, and this is observational well. Okay, initially this is a here, and the water level is at this level. This is a static level, and we are taking continuously water from this. Okay, and this particular well located at r naught, which is nothing but radius of influence. Suppose this observation well located at a radius of influence, located at a distance r naught from the observational well, and here, and in this case we know this SW drawdown in this particular case. So in suppose in this scenario, how we can this is a special case considered by a theme and formulated this equation. So this particular equation is popular after his name. So it is called as a Thames equation, which is nothing but 2 pi into kb into SW drawdown in the well. So here S2 will be 0 because we are looking at an observational well where drawdown is 0, and the R2 will be radius of influence and R1 will be the well. R1 will be the radius of L. So this is an important formula. This is the formula we need to you need to remember for the GATE exam, and all these earlier formulas are useful for other PSUs like IES and other exams. Okay, this is a straightforward. Where what is the terms? There is a drawdown in the well. SW is the drawdown in the well, and R naught is the radius of influence, and R small rw will be radius of well, and K is the hydraulic conductivity, B is the width of aquifer, R slash depth of aquifer, QQ is the discharge, R pumping rate. Okay, so these are the terms to be remembered. Okay, let's solve one some really good question which came gate 2021 set 1. Okay, read this question together with me. A tube well of 20 centimeter diameter. So here it is given in the diameter, so we need to convert into radius of well. Okay, fully I see one assumption is that all this pumping well as well as observation well should be fully penetrated into the confined aquifers, and a horizontal homogeneous isotropic. See, all these things terms are we made as assumptions before. Okay, before solving this particular before deriving the equation. Isotropic confined aquifer. Confined aquifer means both the sides are confined. Both the sides are confined of infinite. See, all these terms are we made as assumptions. Infinite horizontal extent. Suppose one can say that a non-homogeneous, one can say that finite length. So in this case, the question, the entire solution will be changed, and as well as the equations to be used also will be differ. So there are special cases whereas like one end some hill is there, another end is infinite extent. So in that case, you need to use a different condition like this. You need to clearly read the question. And the aquifer is of, sorry, this is a 30 meter uniform thickness, a steady pumping rate at the 40 kilometer per second from the well. So from the well they are taking at a rate of 40 liters per second for a long time, which result into the steady drawdown. So what is a steady drawdown? Steady drawdown means like how much over the water you are taking from the aquifer, the same amount of water will be entering into the well. So the drawdown will be 4 centimeter at the wall face. Okay. The subsurface flow to the well due to the pumping is steady, as I mentioned, and horizontal as well as I told you. See, all these terms are mentioned like are we made an assumptions. The flow is horizontal and Darcy's law is valid, and other things, and has a radius of influences 245 meter. So now the question is that what is the K? What is the hydraulic conductivity of this aquifer? So what they have given. Okay, let me draw here. This is the confined aquifer. This is the confined aquifer. Okay, now there is sorry, there is an observational well here. So this is a pumping well, as I mentioned. Now we are taking Q water from here, and this is a observational well. Okay, so this is a study water level after a long time. Okay, this is the initial level, initial static water level, initial static water level. Okay, and from this level to this well is a distance or not. Okay, and flow is entering here, from all the direction radial. Okay, and this will be B, which is nothing but 30 meters. Okay, and what is the well thickness? The well diameter is 20 centimeter. So, and with, okay, this is a condition, and this is also they have given 4 meter SW. Now they wanted to know what is hydraulic conductivity. What is the hydraulic conductivity of this particular aquifer? Can anybody? So I'll write the equation here only. 2 pi k b, okay, SW divided by ln into capital R naught divided by small rw. So anybody guess the answer? How much is a k? So how much is a k? Can anybody guess? Like read. See, formula is here only, and given data is also here. Just substitute in that. Just it is like 2 marks question. Just to be, if you know this particular formula, if you know this particular formula, you'll able to score 2 marks here. Okay. Okay.
3.77 into 10 power minus 4.
How much? 8 point
3.77 into 10 power minus 4.
minus 4. What are the units? Meter per second or a meter per day? See, that is a mistake we make. See, in this here, they asked to compute in a meter per day and to round it off to integer as well. Okay, very nice, very nice attempt. Let's see the question how we can solve. Okay, so what are the given data? So radius of L can be calculated as 20 by 2. So diameter is given as 20. 20 by 2 is a 10 centimeter. Okay, aquifer thickness they have. So this is sorry, this is 30 meters, not 30 centimeters. So 30 meters. And what is the pumping rate? 40 liters per second. So now we can, so we need to convert it into meter cube. So 1 meter cube equal to 1000 liters. Okay, so obviously 1 liter equal to 10 power minus 3 meter cube. So by substituting that, we'll get a 0.04 meter cube per second. Okay, and what is the study drawn they have given? SW equal to 4 meters, and radius of influence is 245 meter. So this is the formula. Okay, and oh, I forgot to mention this is one more term here. So the product of K and B is called as a transmissibility. Okay, this is a property of aquifer that we can discuss in the further sessions. So this is not much important, but if somebody asks what to calculate the transmissibility, it is just a product of hydraulic conductivity into the width of aquifer. Okay. Okay. So now our interest is to calculate the K. So what we do, just reshuffle the terms. So it will be like Q into ln of R naught by Rw divided by 2 pi into B into SW. So we know all these terms, just substitute here. So K equal to 0.04 meter cube per second into, this is natural logarithm. So natural logarithm. Okay, not, this means that log of E, not log of 10. Okay, you just keep in that mind. Ln of 245 meter divided by zero point 0.1 meter. Okay, zero point 0.1 meter, zero point 0.1 meter, because it's centimeter, so we convert into meters, divided by 2 into pi into width of aquifer B, how much? 30 meter into SW 4 meters. So we'll get as a value of 0.00415 meter per second. So but they have asked to calculate into meter per day. So how you'll do? So 0.045 into 24 into 60 into 60. So by doing that, you will get this particular value. So remember this 24 into 6 by 660, you can remember always, like it is like 846 864 into double zero. Okay, this can be remembered. I hope it is clear. Okay, You can verify this answer. Okay, answer will be 35 point. So answer is 35.88 meter per day. That is a hydraulic conductor to this particular aquifer. So okay, quickly we'll see this particular question. It came in gate 2018 set 2. So, so okay. Now, just now we have seen the confined aquifer. Like for confined aquifer, what we did, we use the Thames equations. Thames equation. Okay. Similarly, this is for confined aquifer. Okay. Similarly, Dupitt has developed one equation, one famous equation for unconfined aquifer. Okay. So that we can see in the further next session. So here the Dupitt assumptions are valid for so unconfined aquifer. This is one more question. One more question. It is in gate 2018. Okay, just remember Dupitt equation is for unconfined aquifer, Thames equation for the confined aquifer. Okay, so that is all I wanted to discuss with you for today. So if you have anything you can ask. So in the next session, the next session syllabus will be uploaded in the website. So, but in the next session we'll see the hydraulic jump. We'll talk about the hydraulic jump. So we will start with the basics, and we'll derive few equations, and we'll talk about the sequential depths, subcritical flow, supercritical flow, and other things. Okay, so in the similar manner we will solve two or three gate questions. So I'll pick up the most important model, and I'll solve the two questions, and you can guarantee that if the question is coming from hydraulic jump, it will be around this particular model only. Okay, and the next session will be precipitation analysis. So for until this month I'll upload the syllabus into the website. You can follow it up. So in the next session will be on hydraulic jump, and for the second next to next session will be on precipitation analysis, where we look at the normal ratio method and averaging method and all. Okay, so thanks for joining this session. So if you have any doubts you can ask me, otherwise you can leave.